I think we're hitting 6, 7 Eastern. So I'm going to go ahead and get started. Thanks everybody for joining us tonight on the RSES Technical Webinar Series. I'm Lori Schiavo, the Senior Director of Operations here at RSES, and I want to welcome you to Bryn's presentation, which is HVAC System Design Part 1. Get rid of that R, I apologize. This part is going to be focusing on load calculations. So I'm going to read from my script here to introduce Bryn. For those of you who don't know Bryn Cooksey, he has been in the HVACR industry for more than 20 years. He's currently the owner and general manager of Air Doctors Heating and Cooling. In addition, he's also an associate professor with Washtenaw Community College in Ann Arbor, Michigan. Bryn is also a training consultant for mechanical contractors, HVACR supply distributors, weatherization agencies, and HVACR training organizations through his company HVACU. In addition to holding many degrees and certification, he was recently named a top 25 HVACR industry's most influential educator and trainer by ESCO Group. And most recently, which everyone will find out about soon, he was named as the ACHR News' top 40 under 40 industry professionals. Tonight's presentation is going to be about 45 minutes, and then we'll have a quick Q&A at the end. The session is being recorded, and those in attendance will be receiving one CEH certificate for continuing education at the end of the session. So those of you who have questions, you can put them in the dialog box from the question side of things, and I will get those answered at the end. But for now, I'm going to turn it over to Bryn. Get the screen to you.
All right, thank you, Lori.
Sure.
Let's pull up our presentation up here. All right, Lori, can you see my screen all right?
Yep, it looks great.
All right, good evening, everybody. Once again, my name is Bryn Cooksey, and welcome to our webinar tonight. Tonight, we're going to be talking about HVAC System Design Part 1. This is Part 1 of a presentation series. We're going to be doing Part 2 next month. So tonight, we're going to focus on HVAC load calculations. Pretty important topic, especially as we get more involved with the Inflation Reduction Act and heat pumps. Load calculations are becoming a critical focus, so we're going to hit everything at a really high level tonight. All right, a little bit about me. Like Lori mentioned, I own a home performance contracting business here in Southeast Michigan called Air Doctors Heating and Cooling. We service the Southeast Michigan area to about the Ohio border. And we started as an HVAC contractor, but as we got more involved with building science, we started to add other features like with the weatherization part. So we'll talk about why that's important here in a little bit. Been in the profession a little over 20 years, been teaching for about 15. And as Lori mentioned, I also help other weatherization agencies and all kind of industry partners with technical training. Tonight, we're going to talk about why we should be doing load calcs. That's kind of the most important thing I think you should walk away from this presentation. We're also going to talk about basic energy movement. We're going to talk about building materials and how important they are to the load calc process. We're going to just discuss heat transfer equations, and we're going to talk about the importance of the building shell and how that affects the load calculation process. And then at the end, we're going to give you some recommendations on how to get maybe technicians in the field or maybe students to understand kind of a foundational part of load calcs that will help them implement it easier. All right, so the focus of this presentation, it is impossible to cover everything about load calcs in an hour. So let's kind of narrow our focus. We're going to talk about calculating heat loss to a building shell, which is a part of the load calc. There's other facets, but just to make it simple, just so we can understand the reason why we should be doing load calcs, that's where our focus is going to be. We're going to talk about conductive heat loss, convective heat loss, and then the benefits of doing a load calc. All right, this presentation was put together with the help of some agencies that we'd like to thank. One is a standardized weatherization curriculum provided by the Department of Labor. The fundamentals of load calculations produced and published by the ESCO Institute, and then an internal study that we did in 2021 that I'm going to discuss the details with you here. All right, so this is a pretty somber statistic. So here in the U.S., we make up about 4% of the world's population, but we consume about 16% of the world's energy supply. And if you look at our picture here, these slices represent our population and how much we're consuming in energy. If you see they're not equal, which means that there is some significant waste, and the HVAC industry has a large role to do with that, and we'll talk about that here in a moment. All right. The HVAC system in most homes or buildings usually account for 45 to 50% or more of the energy consumption in that building. If it's connected to a poorly designed duct system, all right, your system is going to run about 50% efficient. We'll talk about that. So for every dollar you spend on utility costs, the customer is only going to get 40% of the usable energy. This kind of connects the dots on that previous slide that we saw, where we're 4% of the world's population, but we're consuming about 16, some cases, some government agencies say even 25%. All right. So here is a study that we conducted in 2021, coming out of COVID. Everybody was home, they're working from home, and they were more in tune with their personal comfort systems. That hot room where they didn't spend a lot of time in, maybe that family redesignated that as their office. So in COVID, our business grew. And one of the things that people were concerned about was their HVAC systems. And when our business grew, we had some enlightening statistics that we'll share with you. All right. So in that study in 2021, we surveyed about 3,800 homes that we were personally in. And these were clients from our contracting business. And regardless of what we were in the home for, we will ask the client if we can take some measurements, and we performed a load calc and we compared it to the equipment that was installed in that customer's home. When we analyzed the data, 98% of those 3,800 homes, roughly about 3,802 homes, had grossly oversized equipment. So for the furnace, it was 20,000 BTUs or more, and for the air conditioners, they were about 1 ton or greater oversized. And we also looked at the duct system, is what we're going to talk about next month. Those ducts were undersized by 50% or more. So as you see, this is a huge problem. We're going to talk about some specifics here. All right. So here's what we did. When a job was contracted with us, a typical example, this was one of our most common replacements. We will pull out 120,000 BTU per hour furnace, category 1, roughly about 80%. We will replace it with a 60,000 BTU per hour, category 4. And when we crunch the numbers, we would look at the client's utility bills and then compare them a year later. So we would get a year's worth of utility bills on the front end. And then after that year, we would get another year's worth, and we compared them. And on average, those customers were saving about $1,150 per year. All right. During the same time frame, we were interested in what kind of customer complaints were we getting? Were we getting any customers who were saying this significant reduction in equipment size? Were customers complaining that their equipment was not sized correctly? And we had 0, not 1, out of those customers that we served. Okay, when we look at the air conditioning, our typical replacement, when we crunched our numbers, we were converting a 4-ton unit, which is about 10 SEER most often, and then we will replace it with a 3-ton, and the choice at that time was 16 SEER that a lot of customers opted for. And in Detroit's market and climate, the customer saved about $101 per year when they replaced their air conditioner. Now, I want to put that into context. Here locally in Michigan, we're a relatively cooler climate. We have more heating hours than cooling hours. So we only run, a joke around Michiganders is we only have about 22 minutes of summer, meaning that our summers are relatively short, 3 months, 4 months tops. So the savings are just not there for the air conditioner. However, they were still grossly sized, and air conditioning is more of a comfort where customers were still making that purchase. Again, 0 complaints. All the customers were pretty much happy with the performance of that. All right. When we came to the duct systems had some common issues. They were undersized by 50% or more. They were not balanced. They were not sealed. The duct seams were not sealed. If the system was in an unconditioned space, most of the systems that we came across were not insulated. The ducts were never cleaned. And then when we would modify the ducts on top of the energy savings of replacing the equipment, for those jobs, the customers typically saw a decrease in the utility consumption about $230. And to put that into context, that savings was based on the consumption from one year compared to another, with the customer understanding that they had to run the equipment the same way that they had been running it. And it had to be ran in a reasonable manner. Maybe if a customer was trying to, in the summertime, achieve some kind of unrealistic temperature, maybe 65 degrees or something like that, something kind of odd, we didn't count that into our calculations. And there was very few situations where that happened. So that is going to be our next month's presentation, to talk about the duct mod, what we did, some of the problems that we solved. All right. So here are the consequences of poor system design. More costly equipment, all right, that you had to install and maintain, and that the manufacturer had to produce. It typically came with a higher operating cost. The ducts had to be physically larger, which increased the cost of the project. And then the equipment has shorter run cycles, which is counterintuitive to most customers. When you have short cycling equipment, that tends to drive your energy bills up, and it actually increases the wear and tear on the equipment, giving a customer maybe large repair bills in the future. And then there were some IAQ concerns, and we'll talk about that more once we get into our duct presentation next month. So let's crunch the numbers on our savings. When we had the savings from just a furnace replacement, air conditioner replacement, properly sized, and a duct repair, all right, the total annual savings for those customers were $1,481 a year. And that's without us even touching the building shell or building envelope. All right. So that was kind of the numbers, and that's kind of set the stage when we start talking about the specifics of why we need to do load calcs. So part 2, we're going to talk about what the savings look like when we included shell modifications. So what a shell modification is, we did something to the actual physical envelope of the building. We did some air sealing, we added attic insulation, we added wall insulation to kind of bring that load down, and the savings even increased. So we talked about the typical replacement of the furnace, and we also talked about, if you see here, the energy saving increased from our initial number for about $1,100 a year to about $1,400 a year. At the air conditioning, remember in Michigan, we don't run our equipment all that often in the summertime. Our annual savings went from about 101 to about 127. So the shell actually did contribute to some energy savings. When we add the savings up with the shell modification, we now come up to about $1,781 a year. And that's what the shell modification is being done. So that's what upgraded attic insulation and air sealing. Now, here's why doing a load calc is extremely important. From a business perspective, when we were able to communicate to customers that we had this capability and that we can help reduce some of their bills, it was a unique selling proposition for us, our contracting business, and it kind of gave us a competitive edge. Maybe our competitors were not maybe looking at necessarily doing this. But look at the financial incentives that exist just by properly sizing and repairing the duct systems in existing homes. So if we look at $1,781 in annual energy savings, and then we look at that total, if you take 1781 and multiply that at 18 years, and the reason why we pick 18 years, ASHRAE has a lifetime expectancy equipment chart, and that chart just basically says how long is a piece of equipment expected to last. When we multiply that by 18 years, and if the customer was to put that into some type of interest-bearing account, For just for numbers' sake, we use 10%. So the energy savings that the customer received by getting the work done, if they were to put that into an account and it gained 10% interest over year, in 18 years, that total value will grow to $81,000. That's what customers are missing by us not doing load calcs and duct design. All right. So I don't know about you, but $81,000 is a significant investment. All right. You can have a college savings. You can add to your retirement account. It can fund 3 weddings. You can buy your favorite sports car, possibly, and it can be a down payment for a home. So not looking at the load calc and duct design can have huge financial implications for customers just by paying a little attention to detail. This is a real scenario that we actually can help our customers understand and realize just by doing it by the book. All right, so let's talk about some excuses. I've been a contractor for many years, and I have personally done it the wrong way. And what some of the excuses that I had, and maybe others will tell me now when we talk about load calcs, is that it's too difficult, it's too time consuming, especially in the summertime when contractors are trying to maximize their opportunities. It's not necessary. We hear that a lot. The software is confusing, and that can be true. Customers won't pay for it, and then not properly trained to perform the task. All right, so a lot of excuses, some valid, but with all the money that's at stake for a customer's family to benefit from, I think we should start doing load calcs. All right, so we are doing a disservice. We know the HVAC system is the most significant energy consuming device in the home. It makes up the most significant part of the utility bills, and we don't have enough training or available training for technicians to feel comfortable and confident. So this webinar is basically to set the stage of doing those load calcs and what for. All right, proper oversight. There's also weak building codes in our neck of the woods in Michigan. Is not really enforced for a contractor to produce a load calc to get the work done. So with that being said, it is the best thing to do for our customers and our economy and our planet. All right, now we're going to get into some load calculation basics. All right, load calculation, we're going to evaluate the envelope. And just to reiterate, we're going to talk with a narrow, specific focus. We just don't have the time to get into a full-blown load calc discussion, but this is just to kind of give us the points of why we should be seeking that additional training. All right, when we talk about heat loss, think heating season. We're talking about BTUs are trying to leave the building shell. All right, it's colder outside, it's warmer inside, that heat transfers the cold. BTUs are going to leave to the building shell. When we talk about heat loss, there's typically 2 concerns that we have with a building shell, and that's what we're going to focus on tonight. We have heat transmission, which is our first one. That's going to be that heat energy traveling through the shell, maybe trying to go through the wall. And then we have air leakage. All right, that temperature difference between inside and outside is going to drive air to leak into and out of the building, which is costly. We'll talk about that here in a moment. When we talk about heat gain, I'd like you to think cooling season. BTUs are going to enter the shell the same way through heat transmission and air leakage. However, we have some other factors that affect the heat gain. We have occupant loads, living, breathing humans. We have plants, people. They all have BTUs that they're emitting that the air conditioning system has to remove. And even your lighting load, that's a load that the air conditioner has to take into account as far as load calc is designed. But remember, for our focus, we're just going to talk about the building shell and some simple calculations just to kind of get your training path started. All right. When we talk about load calculations, there's kind of 2 markets. When I consult for different customers, sometimes they may send me a print or a blueprint. I'll evaluate that blueprint, put it into some software. All the data I need for that new construction project is there in that blueprint. And when I send that back, the customer has the understanding that the building contractor and the HVAC contractor have to put the equipment in correctly. Right? Then we have retrofit. Those are existing houses those houses typically have a system that's installed, maybe or maybe not installed correctly, or maybe the building codes were not as robust then as it is now. Right? So those are our two markets. So new construction, in a perfect world, you'll get a set of floor plans. You can do a load calc. You can do a duct design. The system is installed. It's commissioned. The commissioning verifies that the system design was correct. Everything works. The installation complies with the energy codes. That customer or family that lives in that house, generations to come, they're all enjoying that. That's the perfect solution. Typically, even with new construction, there are some issues. Right? And then you have replacement systems. We have more of an older housing stock in our country than new construction. So this is where the focus is when you hear things like the Inflation Reduction Act. So with our older housing stock, we have old houses, old multifamily buildings, older buildings in general. A load calc probably wasn't done. A duct design probably wasn't done, depending how old and how robust the building codes were in that area. The system probably wasn't commissioned or balanced. Older building codes maybe had leaking ducts. Leakier building construction, maybe no insulation or insufficient insulation. Right? I want you to look at this slide and kind of understand what an older housing stock, when we talk about rules of thumb, because of these older generations and different construction codes, there really is no such thing as a rule of thumb for load calculations. Right? So as some contractors got into the box swapping bad habit. And what they did by that, they would take the existing equipment for an existing home and they would replace it with similar size equipment. Okay. Typically, if the load calc and duct design wasn't done, we just set that customer up for large utility bills and wasted energy and wasted money. All right, they can't buy those investments that they could have if they had a properly designed system. So improper equipment size and proper duct design, not properly commissioned or balanced. Once again, that's a weakness for our businesses, HVAC industry as a whole, but it's starting to get better. And then this improper system design, we probably replaced that equipment for a reason. Maybe that compressor failed on that air conditioner. Maybe that heat exchanger failed. In either case, it probably was due to improper load calc and duct design. So those are the fundamentals. All right. We replaced the equipment with a similar size, and we started that vicious cycle all over again. So that new family is going to suffer the same consequences. All right. So with that being said, well, what we know now, there are no rules of thumb. When I first got into the industry, I learned some rules of thumb that I used, and they were not correct. One common one you might hear for air conditioning is 600 square feet per ton. And with a moderately weatherized house, an air conditioner can probably achieve 1,100 square feet per ton. All right. This 600 square feet per ton does not have any reference points. It doesn't give you anything as far as insulation value. It doesn't speak to air leakage. So it is a completely wrong rule of thumb. You cannot use that to verify a load calc. And we're going to talk about why. You'll see why in a moment. Another common rule of thumb that many contractors or we learned kind of growing up, kind of tribal knowledge, was 52 BTUs per hour for square foot. And I've seen a lot of contractors actually take this number and design furnaces that way. And we'll crush the numbers. If a building has attic insulation and wall insulation, we're going to see quite the contrast. All right. So every building is different. You have to look at it. You have to look at that building, and assumptions should be avoided at all costs. All right. Now, when I consult contractors or trade schools and we talk about load calculations, a lot of times many people want to go out and grab a software program. Software programs are absolutely wonderful, but I think just from a fundamental and practical standpoint, all technicians should learn how to do load calcs by hand first. So that way they can verify if the load calc program is actually producing the numbers that they expect. Because garbage in, garbage out, The software programs do not have the capability to take bad inputs and convert that into decent load calculation numbers. So if you don't put that input in correctly, then it's going to give you bad data. So the software is only as good as its input. Right? Techs and contractors, like we said, should be familiar with the fundamentals and the formulas with load calculations just to verify their accuracy. Here are several calculations on the market of very fine products. They all work to evaluate a structure and to produce some type of load. Now, as you all are on this webinar, you may live in an area of the country where load calculation is heavily, I'll say, scrutinized by the authority having jurisdiction. So before you make a decision on purchasing one, ACCA approved load calculation software may be required in order for you to kind of appease the authority having jurisdiction. My take is if you live in an area where that's not the case, doing a load calc is going to do you justice on that customer. When we talk about an ACCA approved, they have certain design criteria that you have to make or meet when you size that equipment. So just take that into account. Each and every location is different. All right, so now we're going to quantify the envelope energy loss. All right, so where does your heat go? This is a typical picture of a house here. And as you see these red arrows here? This is a popular picture. You may have seen it before, and it's from Energy Star. And it basically just outlines where your heat energy is going. And in this situation, we're looking specifically at air leakage. So on this air leakage, see these red arrows here? What this is indicating is that your heating and cooling equipment has conditioned some air. All right, that air has migrated up to maybe the upper floors of your building, and it is leaking out. You see this dollar sign here? Maybe it's leaking out through a recessed light or a chimney chase. Maybe it's leaking through the attic hatch. All right, as air leaks out, one of the rules of thumb for building science is that for every CFM that leaks out, 1 CFM leaks in. So I paid the utility costs to heat up that air, and as that air gets heated up and it migrates up, if it leaks out the building shell, guess what? Air has to leak in. Now that air that leaks in, guess what? It's not conditioned, it's not clean, it's not humidified, it's not filtered. We have to pay to get the air to the required comfort levels so that the building occupants are satisfied. So this is a vicious cycle. And what we learn, the older the building is, the more air leakage issues we have. Right? So we have two considerations for talking about envelope losses. As we just mentioned, air leakage. The other is thermal boundary. The thermal boundary is basically your insulation. And this is a visible inspection or visual inspection. Do we have insulation? Yes or no? And if so, how much? And that's going to play a part into our load calculation. All right. So load calc simplified. We need to identify the building materials, the quantity and the type. We need to take measurements of the building shell or envelope. Area and perimeter are two common measurements we take. And then we're going to model that information based on the climate data where we're located in. All right. For example, in Michigan, we have more heating hours as compared to Florida. So their heating load calculation is going to be a little bit different. We're going to take our measurements of the building structure with the inputs of what type of building materials it has, and we're going to model that based on historic climate data. All right. As we get into more of our discussion, we need to kind of get some terminology down. All right. First thing we want to talk about, we're going to use the term BTUs per hour. All right. This is the power measurement for HVAC equipment, and that's how we're going to describe heat transmission. All right. When you see heating degree day, we're going to basically use that to describe climate. All right. Describe climate. And then R value we're going to talk about is resistance to conductive heat transfer. Every building product has some type of R value. So when we talk about R value, I want you to think insulation. Here's a picture of what heating degree days look like based on the climate. So here in Michigan, we're around 63, 48, kind of this area here. as you see in Florida, the South Atlantic, they don't have as harsh as winters as we do in Michigan, so their heating degree days are a little bit different. All right. So with that being said, the load calculation rules of thumb really don't work because one of the climate. What happens to work in one climate may not work in the other. And in some situations, you might even have microclimates within the same area. For example, if the property that you're evaluating is near a lake, it may have actually a different heating or cooling requirement. So you have to keep that in mind. All right. Here are some typical R values of building materials that we use. We see we have fiberglass. Average fiberglass number that we use is 3.5 per inch. You see that we have cellulose. Cellulose is another building product that's quite popular. That's around 3 per inch. And then you have different types of foam boards. You got expanded polystyrene, 3.6, extruded about 5. You have glass and wood and concrete. You also have polyiso. These are common building materials that we use that we have to account for because these are inputs into our load calculation software, and they all have different R values. So that busts another myth about rules of thumb. You have to know what your building materials are in order to properly do a load calc. All right. When considering a building, one thing we have to look at is the assembly of materials. And if you think about a building, maybe the building that you're in, maybe your home, take your nearest wall, outside wall, it typically has a assembly. So maybe we have our outdoor siding, and next to this outdoor siding, there is an air film that has an R value. All right, we have our building wrap. All right, it has an R value. We have our plywood, we have our fiberglass, we have framing members, our stud, we have insulation, we have our interior sheetrock, maybe plaster, and then we also have an R value of air film inside. All this is a composite assembly that the heat flow has to either transmit from outside to in or inside to out, depending on whether we're in a heating or cooling situation. You have to know these inputs in order to properly do a load calc. So when we look at these inputs, another reason why it's important to truly evaluate a building is because there are some constraints that are placed on building, especially building insulation, that can affect our load calculation output. For example, you may have heard of the law of diminishing returns. Quite often when I train new building science professionals and we talk about attic insulation, and they'll say, okay, if attic insulation is so great, why don't we fill the entire cavity with attic insulation? Well, the juice may not be worth the squeeze. General rule of thumb here, for every successive R value, it saves about 50% of the immediate, the prior R value. So what that means is the more insulation I add, the returns actually start to diminish. The heavy lifting for attic insulation is typically done in about the first 6 inches. All right, we have to know and understand that in order to evaluate load calculations. Now, I'll pause here for a moment and let you take a picture of the screen here. This is a absolutely very, very important calculations that we need to understand for load calcs. All right, so quantifying our envelope losses, we have 2 formulas here. We have our surface heat loss, or I'll call our conductive heat loss, which is the area, length times width of what we're trying to measure. The delta T, the temperature difference between the two surfaces. The time, and then the resistance of that assembly flow that we just talked about. You may have also seen this formula represented as UA delta T. It's describing the same information as this formula is, but just for our context, this is the formula that's describing heat transmission through a building wall or maybe a ceiling. Okay. The second one, which cannot be used with a rule of thumb, or evaluated really without a certain tool called a blower door is air transported heating loss. All right, this is that air leakage that we were talking about. And that air leakage has a formula too. Our load calcs are really not accurate unless we know what that heat loss is through air leakage. All right, so it's the volume of the building times the air changing hours times the specific heat of air times the delta T. Okay, this gives you the BTUs per hour heat loss that occurred through air leakage. Right. So let's do an example. Right now, we're going to talk about a simple wall surface that we're going to measure. This wall doesn't have any windows, and we're just going to come up with some BTUs of heat loss through that particular structure. All right, so our wall section is 8 feet by 12 feet. All right, no windows in this case. We're about 96 square feet. In this particular example, we have an inside temperature of 70 degrees and 30 degrees outside. So we have a 40-degree delta T. Right. Also, in this situation, we're going to describe a climate having about 7,200 heating degree days. So we're talking about a relatively cold climate. And the R value of the assembly is a R10. All right, so we're going to calculate the BTUs per hour going through that surface, and then also the heating season. All right, here's how our math breaks out. All right, the BTU per hour for the surface is 384 BTUs per hour. That's based on a 96 square foot wall section with a 40-degree delta T, and then times 1 hour divided by our hour value of the wall assembly. All right, 348 BTUs per hour. When we look at it over a heating season, we're taking the climate into account. Remember, this is a relatively cool climate. All right, we're coming up with 1.6 million, all right, BTUs. All right, this is important if you're going to do a little bit of energy modeling, if that's a part of your business function to do energy modeling. It would be important to know how many BTUs are going to be produced on that surface per season, and maybe you can predict what the energy savings is going to be. Some software calculations do that for you. All right, now we really can't look at a building and come up with a rule of thumb as far as square footage, as far as insulation. You physically have to look. You really can't describe a building's air leakage by looking at it. An older house may be weatherized and it's just an older house. So the most direct way to evaluate air leakage is to perform a blower door test. What a blower door is a device, it's a large fan that you hook up to an airtight enclosure. And basically what you do, you can either pressurize or depressurize a house, with depressurizing being the most common test. You're going to evacuate the air out of the house, and what our building science principle of 1 CFM out, 1 CFM in, as the air is being evacuated from the house, air from outside is going to come through the imperfections in the building shell. So those gaps, cracks, and holes, air is going to leak back in. The blower door is going to maintain a test pressure that we're going to talk about in pascals. When we use a blower door, we're going to use it with a manometer, and that manometer, it can't be a manometer that is used to measure maybe static pressure or maybe gas pressure. We have to use a micromanometer that's capable of measuring pascals. All right, and here's why. 1 pascal is about the weight of a Post-it note. 249 pascals are equal to 1 inch of water column, and 1 inch of water column is the pressure required to pull up like a drink through a 1/2 inch straw. Okay, so we're dealing with very, very small pressures that I'll say standard gauges may not have the resolution or the units of scale to measure the pressures we're trying to obtain with the blower door. All right. When we're measuring the blower door, that blower door is going to produce an airflow, a leakage rate that we're going to calculate with the blower door itself in conjunction with a manometer, a micromanometer. All right, and based on the size of the house and the number of occupants, we come up with kind of a standard. Now, with blower door testing, the way it works, the higher the leakage number, the more leaky the house is. It's quite that simple. To compare houses on a like-for-like basis, blower door testing comes associated with a standard test pressure called CFM 50. What that test pressure is for, I can evaluate one residence and another residence and another residence, and if I all test them at that same test pressure, I can equally evaluate the leakage rate between them. So it gives me a reference point to tell who's leakier, who has less leakage, and so on and so forth. All right. The blower door, this fan is going to depressurize in most cases to create a negative 50 test pressure. So quite truly, there's going to be a pressure difference of negative 50 pascals between inside and outside. Now, the blower door itself is a fan that we connect to this airtight canvas enclosure, and this technician here has a manometer. And this manometer here is going to actually measure the pressure differential between outside and inside, and it's going to measure the differential across the fan here, and we're going to be able to calculate airflow. All right. So here's the fan. Another reason why you can't use rules of thumb, if you see these rings here, these rings are designed for different buildings. All right, so see how this B ring is smaller than this A ring. With this load calculation, this input working with this fan, if I have a larger ring, that means leakier house. If I have a smaller ring, maybe that house is a little bit tighter. You won't know what rings those use until you actually perform the blower door test. All right, so it's a real critical piece for load calculations. Also with the blower door, there is a frame or shroud that you assemble to fit into any exterior door in order to perform your test. Okay. And with that frame and the fan, it all reports to a manometer. So this is a more updated version of the manometer that that technician had. And with this blower door, this manometer, excuse me, this is going to maintain the test pressure for that fan. And it's also going to give you the flow of that building. And the way it works, the higher the CFM number right here, the leakier the house. Right? We take this input or a modified version of this input, and we're going to put that into our load calculation software. Once again, this is more accurate than coming up with some type of description like a loose or semi-loose or tight. We can't determine what those actual values mean without testing. Right? So it's a much more accurate way to fine-tune your loads. All right, when we set up a blower door, we're going to put it in any exterior door. All right, we're going to put the house in wintertime conditions. Basically, what that means is all the interior doors are going to be open, all the exterior doors are going to be closed, all the windows are going to be closed. And we're going to put that fan in one exterior door that we plan to use. We're going to turn off all our combustion equipment, so disabling our water heaters, disabling our heating and cooling systems. We're going to turn those off. If you have a fireplace, you're going to close that damper. You're going to make sure no wood stoves are in use. And then if there was an active fireplace, if you're going to perform a blower door, it's a really, really good idea to put that fire out and then also let it cool, and then maybe to put wet newspaper over the ambers so that those ambers are not pulled in when you conduct the blower door test. All right. Here's how it works. Inside this blower door, it has a flow sensor, and a manometer is going to be comparing the pressures from the inside the fan in the house, and it has a reference pressure to outside. And we're typically going to depressurize the blower door here. We're going to that's the most often test. The fan can be turned around and the tubing reconfigured to perform a pressurization test, but most often it is in depressurized mode. So air is going to be leaving the building, and it's going to come back to those gaps, cracks, and holes, and a manometer is going to measure the pressures and calculate a CFM 50 number. The higher the CFM 50 number, the leakier the house, the bigger my load for heating, the bigger my load for cooling. Now, there's a couple of things that you can do with a blower door. One, you can kind of determine an approximate leakage area of the holes in the house. Now, if you are sitting in your house and you're looking around and you're saying, what holes? We're talking micro cracks. We're looking at very small imperfections in the building shell that you probably can't see. All right. But if we were to run a blower door and come up with the CFM50 number, like so, like this 5,000 here, if we were to divide that number by 10, that gives us an approximate square inch number that will help us determine if I was to add all the leaks in the building up together, how big will my hole be? All right, so a 5,000 CFM50 blower door is roughly a 500 square inch hole, or roughly 25 by 20, which is a pretty substantial hole, which helped us communicate to the customers why some shell modifications needed to be done. All right. Now, some software programs may require you to use what are called air changes per hour. What air changes per hour is still utilizing that 50 Pascal test pressure, but a CFM50 number gives me leakage, but it doesn't really tell me how leaky that building shell is. In order to get a true number of how leaky that building shell is, I have to take the building's volume into account. And what we do, we have a formula for that. All right, so if we take ACH50, which some software programs may ask for, we're taking a CFM50 number that is produced by the blower door and a manometer. And if we multiply that by 60 minutes per hour, we're going to come up with a number. And then we're going to divide that by the house volume. And that gives us ACH50. All right. Here is a kind of what we've experienced to be most common, and we probably need to change as our energy codes are becoming more strict. When we say a new house, typically you're going to see 5 to 10 air changes per hour. This is becoming more aggressive. Now in the state of Michigan, to build a new house, it has to achieve a blower door number of 4 air changes per hour. Some parts of the U.S. are 2 or 3 air changes per hour. So they're getting more and more aggressive as far as air changes per hour. When we deal with an older house, I'll say maybe 30 years and older, we typically see 11 to 15 air changes per hour. So relatively leaky, a lot of air that has to be conditioned and dealt with bigger equipment that we have because we have more BTUs. Some houses are up to 30 air changes per hour. All right. Some houses are so leaky that we have to use a blower door, maybe with multiple fans, just to get it up to 50 pascals test pressure. So you're talking about some serious leakage. Without doing a blower door test, you won't know what your air leakage is, and it will be a pure guess if you describe it by something else than what the actual leakage rate is. All right. So here's an example of how we use it, kind of a practical example. All right, we have air changes per hour at 50 pascals. We have the house volume, which we come up with length times width times height. In our example here, we'll keep it simple. We'll use a conditioned ranch that's on the slab. All right, when we use our volume, we're only going to deal with the conditioned space only. That's the only thing we're going to calculate. This may or may not mean the basement. If the basement is conditioned, that means it has to be accounted into the building volume. If it's not, then it's not. So if it's conditioned, you have to include the basement in a conditioned space calculation. All right, for this house, the example, we have 40 foot long, 28 feet wide, and 8 feet high, 8 feet ceilings. Our blower door calculation was 4,500 CFM50. All right, if we take 4,500 times 60, and we divide that by the house volume, which is 8960, this house has 30 air changes per hour at 50 pascals. So relatively leaky. Without doing a blower door calculation for your load calc, you are guessing. All right. Now, some calculations or software programs may want you to get ACH natural. All right, ACH natural. ACH natural is without the influence of the blower door, we're looking at natural air pressures. Now, natural air pressures are tough to measure because they're very low and they're inconsistent. So we use a blower door to exaggerate the pressure, and then we'll back calculate to what that natural pressure would be. So at an ACH 50, we talked about converting that. We take the CFM 50 times 60, multiply that together, and then divide by the building volume. All right. If we want to get to natural from ACH 50 to ACH natural, we take the ACH 50 number and divide it by 20. Right? Divide it by 20. And some calculations actually require the ACH natural. So it kind of depends on which software program you're going to be using. All right. So let's do a load calc. Let's go through some examples here. All right. First off, we're going to talk about an uninsulated ranch. All right. Let's keep it simple. And remember, we're going to talk about the context of actually the building shell. All right. So with our building shell, we have 20 feet by 30, and it's on a slab. So it has 8-foot ceilings. So this is going to give us our volume here. All right, 10% of the wall area is used for windows and doors. We're going to put it into a climate that is around 7,200 heating degree days. We have a 40-degree delta T, and right now we have no insulation in the walls or ceiling, and we have a 1.2 air change per hour. All right, natural conditions. All right. All right. So basically, we calculated our volume. All right. So we're 20 by 30, 30 by 8. We have the area of each wall and area of the ceiling. So our rough wall area is 800 square feet. Our windows and doors are 80. All right. Our total, when we take out the actual walls, the windows and doors from the walls, we come up with 720 square feet. All right. And then our ceiling is 20 by 30. So that's the actual number we're going to use for heat transmission through the ceiling. All right. So we're going to do our load calc. All right. And our volume for this equation is going to be 4,800 cubic feet. And we're going to need that for our blower door measurements we're going to talk about here in a second. All right. So let's put it into the formula. So for our uninsulated ranch, we're going to be about 9,600 BTUs. And basically, we took our 720 square feet from the walls by our delta T, and we had an R3, meaning that we didn't have any insulation on the walls. We just simply had the sheetrock and then exterior parts of the shell, maybe the siding. Okay, so 9,600 BTUs. The ceiling, we had 600 square feet multiplied by 40 degrees, and we didn't have any insulation, so we just had the building materials for our value of 1. So we had 24,000 BTUs traveling through the ceiling. Okay? That was the heat loss on the surface. Now let's calculate the air leakage BTU loss. I'm sorry, this is the season. So the BTUs for the season, we're looking at the area times the heating degree day. So 720 times the 7,200 heating degree day times the 24 hours divided by 3, which is our hour value for the walls. All right, per season, we're at 41 million BTUs. And for the ceiling, we're a whopping 103 million BTUs for the ceiling for the season. Remember, the seasonal losses are primarily used for energy modeling software to help calculate return on investment and savings, etc. All right. Heat loss through air infiltration, we got our formula here. All right, so based on a 4,800 cubic feet of our building and a 1.2 air change per hour, all right, times our air density calculation, times the delta T, we came up with 4,300 BTUs per hour. And then if we look at it over a season, right, the air leakage for that building is going to cost us in BTUs 18 million BTUs roughly. All right, so that's an uninsulated house. Now let's compare that with a minimally insulated house. So we're going to take the same parameters, the same house, the same area, the same volume, same 10% windows, the same heating degree day, the same inside and outside temperature. Now we're going to put R11 in the walls, and we're going to put R19 in the attic, and we're going to keep our leakage rate just for an example. All right, so in red, these were our existing BTUs for a house that was not insulated. All right. Now, when we look at our walls, just by adding insulation, we reduced the BTUs from 9,600 BTUs to 2,880, which is pretty significant. All right. The ceiling went from 24,000 BTUs in heat loss to 1,400 just by adding attic insulation. All right. What about the annual? We went from 41 million to 12 million for the walls, and we went from 103 million to 6 million for the attic. All right, significant energy savings just by looking at the shell. Now, if you were to look at the shell and apply a rule of thumb, you would have been wrong just by having just a small amount of insulation. All right, so when we calculate the walls without insulation compared to the walls with insulation, we had a savings of 29 million BTUs per year, excuse me. And when we look at the price of natural gas at a therm across the country is about $1. All right, just the walls would save about $290 just by having the walls insulated. And once the walls are insulated, the energy savings is almost immediate. That's for one wall in the heating mode. Right here, one wall in the heating mode. All right, let's talk about the ceiling. We went from 103 million down to 6 million with a 97 million annual savings in BTUs. Okay, we crunch the numbers by having attic insulation for that home or business. You're looking at almost $1,000 a year in savings, and that's the ceiling BTU consumption only in heating mode. We haven't even talked about cooling mode. All right. And when we talk about the air loss, we didn't change the air infiltration for this example, but it hasn't changed. So now we're going to look at the same scenario. What we added was more attic insulation, and then we're going to have a reduction in air changes per hour. What that means is a professional has went in and professionally air sealed the building. They went into the attic, they sealed plumbing penetrations and electrical penetrations, and they reduced the air leakage so that the BTU stayed into the house longer. So we reduced that air infiltration rate, or we had a smaller blower door number. Right? So that's not going to change our walls because we didn't change the walls. They're still 3.5 inches. But by going from R19 to R38, we went from initially with no insulation, 24,000 BTUs down to 632. A significant energy savings. And we look at the annual. When we look at the airflow changes that we're making, initially we had we talk about reducing the air leakage after it was air sealed. We went from 4,300 BTUs per hour down to 1,200 by sealing up that building. And that's just in the heating mode that we crunched the numbers. We went from 18 million BTUs in the season, almost 19 million, down to 5. All right, significant reductions in energy consumption. All right, so when we did a ceiling evaluation with no insulation, with upgraded insulation to R38, all right, we're saving about 100 million BTUs per year. We crunch the numbers that produces to the average customer, primarily in Michigan, about $1,000 savings to their bottom line. And when we look at air sealing, we saved 13 million BTUs per year. All right, and we look at the cost of our fuel, we're looking at about $136 a year in savings, and that's just in the heating mode. Right? So when we look at load calculations, there are no rules of thumb. We have to evaluate the shell and look at the shell for what it is, and we have to do the proper evaluation, and we have to do testing with the blower door. There are no rules of thumbs that will give you enough data to accurately perform a load calc. And as you see, just but little inputs like adding attic insulation, if you made the replacement of a system without taking those into account, you lock that customer into the same cycle. All right. Now, load calculations could be a difficult topic for technicians to learn or grasp. And what I train and consult other organizations, one of the things I have them do is to break up the load calc process into smaller assignments. If you're an instructor, maybe having your technicians practice gathering information like the area, like volume, like perimeter, And basically, if they can measure and evaluate the proper inputs, whatever software that they use, they'll always get good outputs. And my final suggestion is to have technicians learn about the building materials that they need or they're going to be interacting with. They need to know about the building construction types, the building construction materials, what type of installations in the home, windows, doors, and roofing material. And that brings us to an end to part one, and we're going to turn it over to Lori for questions.
All right, great presentation, Bryn. I have a question about process related to doing the blower door test. So obviously that's on initial, like when you first go out, you do your blower door test. Do you provide the information in the quote right away, or is that a second thing that you have to do once you return to the office?
It depends on the situation. Typically in our business, what we do, if a customer has, I'll give you two examples. If I'm trying to convince a customer to select our business and to perform a load calc and to sell them on the energy efficiency that we have to offer, it may be valuable for that customer to see the blower door process, for them to understand the level of detail we're going into. Some contractors may not be comfortable with that. So because it is a little time consuming, definitely when a job is contracted, we're sending a tech back out to perform the blower door test. And I've seen both ways be successful.
Okay. This question is in regard to the case study that you guys had done. So when your furnaces were replaced with single stage, two stage, or modulating, wait, let me reread this. So when the furnaces were replaced in that case study, were the single stage, two stage, or modulating utilized to reflect the benefits of comfort and savings? So did you break it down?
That's a very good question. And actually, no, we use it as a unique selling proposition, but in that study, we did not specifically break it out. We would have had to do a lot of data logging, and then some customers, maybe we couldn't get a thermostat wire to provide a second stage, and the equipment had to produce the second stage on its own accord through algorithms. So we didn't specifically test that. So I actually believe our numbers are understated. I think we actually did better than what the numbers actually show.
That's a great case study you guys did. Does the ICC, particularly the Michigan Mechanical Code, allow for an infiltration credit versus the ventilation requirements?
Infiltration versus a ventilation requirement. If you can give me their email, I need to ask some supplemental questions about that.
Absolutely. Offline it goes. And for those of you who do have questions, go ahead and ask them now. I have one more right now at the ready. Here they come. Let's see. Give me a sec. Okay. With respect to the air changes per hour when a basement is involved, does it include only the above grade volume of the basement?
No, the total basement. If the basement is conditioned, then total basement volume has to be included. Very good question.
When conducting a blower door test, do you have to block off the furnace, water heater vents, and bathroom and stove vents?
That's a very good question also. General practice, no, because in theory, the exhaust fans are supposed to have a working damper. Sometimes they don't, which will skew it, but it doesn't change it a lot. And then the draft that maybe they're probably referring to like a water heater draft, that's a permanent hole inside the building anyway. So blocking that off wouldn't be simulating real true situations. So again, that's not a lot of air leakage either. So no, we don't go to that extent when we do the blower door test.
Okay. Do you guys ever do, I saw a smoke test on the outside of a building showing infiltration. Do you guys ever do any of that as well?
Yes, we
to
do.
show them?
We do fog. Absolutely. We use a fogger to help identify where the leaks are. And then the blower door test is a great tool used in conjunction with a thermal imaging camera. It will definitely help you find air leaks and voids in insulation.
That's amazing. You'd be surprised where the smoke goes. It's
Absolutely.
amazing. So it looks like you've answered all the questions. I do want to let people know if you have a question after the fact, you can send it to general@rses.org and I'll make sure Bryn gets it. Or Bryn, I don't know if you want direct, but I can filter that for you.
Yep, they can reach out to me directly. My email is bryn@hvactrain.com. So BRYNN at hvactrain.com, and we can continue our discussion, and then we can talk about other ways where we can pick up the training to talk about load calculations.
That's very cool. Okay, so I'm going to go ahead and take the screen back and just do a quick wrap up. Bryn, thank you so much for taking the time to present this topic. I know it's so important. Oh, one more question before I do wrap it up. Do you have a good resource for states that are providing tax credits for people who are upgrading their systems?
Yes, we're going to be producing an article that's going to be talking about the Inflation Reduction Act, how it's going to affect different market segments, and how contractors to take advantage of it. So look out, and it'll probably be published through RSES.
Perfect. I love that. Okay, let's see. Let me try again to take it back. I don't think it's letting me. All right, well, just pretend I have a screen up that says Bryn is awesome, okay? So I just want to thank everybody for attending the session and for Bryn for taking the time to present it, of course. For those of you who want to review the session at a later date, you can do it by going to rses.org and then hovering over the training menu item at the top, and you'll see the webinar archives. You do have to be logged in as a member in order to view those, but we have your probably from 2013 to current archived right now. People who attended this live session, you're going to get one CEH certificate. It should happen as soon as I end this meeting. If you do not get it, contact me at general@rses.org and we will get that fixed for you. And again, if there's any questions, you can send it to that same email address or Bryn direct, and we will get it answered for you. All right. So thank you, everybody. Hope you have a great night and hope to see you next month as well. The next one is August 28th. So go to our calendar and sign up, or you can wait for the e-blast. We'll get those to you and you can register that way. All right, everybody. Have a great night.